So yesterday what we were looking at are, I call them base functions. Maybe I should be calling them basic functions. Two basic or base rational functions. One of them is y equals 1 over x. One of them is y equals 1 over x squared. And you need to know what these look like so that you can apply these three parameters to them. We're not worried about the parameter b here. There's various reasons why we don't care. The bottom line is we're only concerned with vertical stretches and or reflections vertically, and then also horizontal translations and vertical translations. Both of these functions on the left have asymptotes that are on the axes. So the horizontal asymptote is at y equals 0. In other words, it's the x-axis. The vertical asymptote is at x equals 0, which is the y-axis. What that means, good morning, Mr. Hetlinger. What that means is that after the stretch or reflection, which is not going to affect the asymptotes, that's going to be distracting for me. After any vertical stretch and or vertical reflection, which doesn't move the asymptotes will only be affected by h and k. So what that really means in the end, without even looking at these graphs, is that you are going to have a vertical asymptote at x equals h, and you are going to have a horizontal asymptote at y equals k. So again, the fact that the reflection and the stretch happens first, if there is a reflection and a stretch, doesn't change the fact that that's where the asymptotes will be. I mean, generally speaking, you need to know what each of these two graphs looks like. Y equals 1 over x. There's actually a name for it. It's called a hyperbola. Y equals 1 over x looks like this. Again, the asymptotes are on the axes. So you have a vertical asymptote here and a horizontal asymptote here. That's y equals 1 over x. When you start talking about y equals 1 over x squared, the squared takes any y coordinates of 1 over x and makes them positive by squaring them, which is going to fold this bottom part of 1 over x, which is in quadrant 3, up into quadrant 2. But the squared also affects the severity of the curve. Things get steeper and shallower. So the end result is y equals 1 over x squared looks, and that might be a gross exaggeration, but you get the idea. It's significantly different shaped than 1 over x. So that being said, does anybody have any questions you would like me to go over or explain here? Ryan? 5b. Okay. So we have to write x over x plus 8 in the form where we have a, h, and k. And traditionally how this is asked on an exam question is I give you that function and I say, what is the series of transformations that it needs to undergo in order to get x over x plus 8 from 1 over x. So we're trying to convert x over x plus 8, Ryan, into a over x minus h plus k. Now, there are different ways that you could do this, but the way that I've taught you is to do synthetic division and divide x plus 8 into the numerator, which is x. And when you do that, you have to put 1 for the degree 1 term, which is x, and you need to put 0 for the constant term, because on the top of this, it's not x plus 3 or x plus 2, it's just x. I bring the first number down, which gives me 1. I multiply these two, which gives me negative 8, and when I add them, I get negative 8. So what does that mean? It means that the quotient, the result of the division, is 1, and the remainder is negative 8. And what that means is you can write this fraction or quotient as the quotient plus the remainder over the divisor. And that's pretty strange because I had to pause there to see if I did something wrong, because I'm getting for A negative 8, and for H I'm getting negative 8, which is a fluke. Okay, so when I rewrite this function, it can be rewritten as negative 8 over x plus 8 plus 1, which means we have a vertical reflection because A is negative 8, and it's vertically stretched by a factor of 8. We have a horizontal shift of 8 units to the left, and then a vertical shift of 1 unit up. Does that make sense? Okay. Other questions? Yeah. 5C. So we're going to be doing the same kind of thing here. We have, whoops, what happened there? Y equals negative x minus 2 over x plus 6. We need to divide x plus 6 into negative x minus 2 to see what we're going to get. When you do synthetic division, you have to, when you're dividing by, for example, grant x plus 6, you have to put the 0 of x plus 6. In other words, you put negative 6 there. We have to put negative 1 for the x to the 1, and we have to put negative 2 for the constant term, and then move the first number down, and now we're ready to do synthetic division. I multiply the negative 6 by the negative 1 and get 6, and then add the negative 2 and the 6 to get 4, which means this is my quotient, and this is my remainder. The remainder statement or quotient theorem or division algorithm, there's all kinds of words for this thing. Ultimately, though, you need to know that when you divide two polynomials, the result is the quotient, which is negative 1, plus the remainder, which is negative 2, over the divisor, which is x plus 6. So I rewrote this. Rather than writing the quotient plus the remainder over the divisor, I put the remainder over the divisor first because I want this to match a over x minus h plus k. Which means a is negative 2, h is negative 3, and k is negative 1. You okay with that? Okay. I don't know how far we want to go with an explanation here. It means that the graph of 1 over x is vertically reflected. It is vertically stretched by a factor of 2. It is shifted 6 units to the left, and it is also shifted 1 unit down. Go ahead, Liam. Is the remainder 4? Oh, my mistake. Why did I put negative 2? Oh, yes, the remainder's 4. Thank you. So it's not reflected vertically. It's stretched vertically by a factor of 2, or 4. Okay. By the way, I think many of you would look up here and automatically see that h is negative 6. So it's possible for you to determine h without actually doing anything. After Monday's class, I'll revisit this and show you that if you use your knowledge of asymptotes, which we haven't really discussed too much, but we will on Monday, if you use your knowledge of asymptotes, you can determine k by looking at this. Okay. You know what? I'll tell you right now. K is always going to be, in these questions, the coefficient of the x on the top divided by the coefficient of the x on the bottom. Always. And what that means is, I guess I can show this to you now, you didn't have to do this if you can figure out that h is negative 6 k is -1 because of this rule I'm giving you, divide the coefficients. Then you can put those in and have a over x minus h plus k, and now you have an equation with a missing parameter. So how do you get an ordered pair? I don't know. Make a table of values. Choose -5 for x. Anybody know why I'm choosing -5 for x? Choosing -5 for x because when I put it in the denominator, -5 plus 6 is just 1. I'm not dealing with a fraction. And when I put -5 on the top, I end up with negative -5 minus 2. That's interesting. Oh, I end up with -5 minus 2, which is 3. So I have to put 3 here. This becomes 1 on the bottom. And you can solve now for a by adding 1 to both sides and get 4. So there's other ways you can kind of maneuver your way around this question. Any other questions? Okay, so we're going to move on today and look at what's called analyzing rational functions. This is in section 9.2 of your textbook. And we're going to analyze rational functions of any form. So these functions we started looking at yesterday, y equals 1 over x and y equals 1 over x squared, are very simplistic rational functions. They're going to get more complicated because don't forget, a rational function is any function where you have a polynomial over a polynomial, as long as there's x in the denominator. We're going to be focusing today on non-permissible values. A non-permissible value of the variable x will be some value of x that makes division by 0 happen, which is not allowed. But when you have a non-permissible value, one of two things will happen. You will either get a vertical asymptote or you will get what's called a hole in the graph. And a hole can also be thought of as a point of discontinuity. So example 1 says consider the rational functions, and I'm giving you 2 of them, and it asks for the non-permissible value of x in each one. So I want everybody to look at those 2 rational functions and record in the blank the value of x that would not be allowed for f of x and the value of x that would not be allowed for g of x. It's 2, right? Okay, that's pretty basic. So we have 2 rational functions. They really kind of look the same, don't they? They have a quadratic over a binomial. They have the same non-permissible value. Now it says sketch the graphs of f of x and g of x using a graphing calculator. So I'm going to start with f of x. And you should be doing the same thing. We have y equals, you need to put that trinomial in brackets, x squared minus 8x plus 15. And then we're going to divide that by, in brackets, x minus 2. And I don't think we want to graph them both on the same grid. Let's just graph them one at a time, please. I better go zoom standard. And we're not going to get lost in we don't want to get lost in the really wavy, curvy, bizarre nature of this graph. What we want to focus on is the asymptote. And I need to discuss with you what's going on your graphing calculator when it draws that jagged line that's kind of vertical. What your calculator does when it plots a graph is it takes an x coordinate, calculates y, and then it moves on a little bit to the right of that x coordinate and it picks a new x coordinate and it calculates y. And on this graph, there is going to be a vertical asymptote at x equals 2 because of the non-permissible value. When your calculator calculates a value of y for a number like x equals 1.999, it gets a point that's very, very negative. It gets a very large negative result for y. And when your calculator moves past 2 and maybe uses an x coordinate of 2.001, it gets a very large y coordinate. And I haven't done justice to where those 2 points are. They are extremely far apart from each other. But when my calculator goes from x equals 1.999 to x equals 2.001, it's not plotting. When your calculator plots a graph, it's not plotting an infinite number of points. It's plotting a bunch of points and then it's connecting them. But the points are so close together that you don't see jagged lines. Except these 2 points are really close together horizontally, but they're really far apart vertically, and the calculator tries to connect them. This is not the calculator drawing the asymptote. It's a flaw in the programming of the calculator. However, that being said, we can sketch what this function looks like. The asymptote is at x equals 2. There is a part of the curve that looks like this. And there is another part of the curve. I'll look a little carefully here, way down there. It looks like this. But that's what it looks like in general. And again, I don't want us to get lost in all the details of the weird curve to this in Math 31. Those of you that take calculus, please don't draw this. We will learn that there is something called a slant asymptote, and that both of these curves are going to be getting closer and closer to that angular asymptote. We don't need to worry about that here, but I'm just pointing it out for those of you that will take calculus. Now let's draw on our calculator g of x. So any questions with f of x? Okay. So now we're going to plot g of x. And it is x squared minus 3x plus 2 over x minus 2. And I think I'm still at zoom 6, but I'll do it again just in case. And what we see is a line. But hang on a second here. We said that x can't equal 2. It's a non-permissible value. And a line has a domain of any real number. So what we can do right now, just as an investigation, is if I go trace, I can enter an x coordinate. So I'm going to go trace 4, and I get a y coordinate of 3. If I go trace 2, I don't get a y coordinate because there is no point there. This is weird, because if I go trace 1.9999, I get a y coordinate. If I go trace 2.0001, I get a y coordinate. You'll notice that on the other graph, if I did 1.999, I'd get a very large negative number. And I regret not doing that at the time on the calculator to show that to you. And when I put on the other graph 2.001, I get a large positive number. So with the first function, as we get closer to that value of x that's not allowed, the y coordinate takes off. Here, the y coordinate is settling down. So there's a hole in the line, and the size of the hole in the line is infinitely small. but it's there. Okay. You can see the hole if you go zoom decimal. Don't ask why. I could explain it, but it's not important. If you go zoom decimal, a lot of the time your calculator will show you the opening in the graph. But that's not a very good representation of what's going on, because that opening is infinitely small, which is why you really ought not to be able to see it. So what does this look like? It is a line that goes through 1 on the x-axis, -1 on the y-axis, but at x equals 2, there's a hole. So when we draw this, we draw it this way. And I suppose we could put arrows on the ends of this. So they both have a non-permissible value at x equals 2, but the behavior of the graph in that region where x equals 2, or surrounding that region near x equals 2, is totally different. Describe the differences between the two with f of x as x gets closer to 2, y gets extremely large. That's the most succinct way that we can describe that. As x gets closer to 2, y will approach infinity or negative infinity. And by the way, on our graph, is it like this from your perspective with f of x? Okay. It doesn't have to be like that. It could be like this, it could be like this, or it could be like that. So on either side of the non-permissible value, the graph is taking off either to positive or negative infinity. That could be both infinity, both negative, one positive, one negative on the left and right, or switched. Whereas here, with g of x, as x squeezes in on 2, what does y get closer to 2? Now, you've got this on your calculator right now. Use your calculator to try to figure out what the y coordinate is getting closer to as you get closer and closer and closer to x. Jason? 1. Perfect. If you wanted to, if you went trace we'll go 1.9. 1.999999999999999999999. We hit enter, there's still a hole there, right? But if you go to your table and do that, I'm going to change my table to ask, and you go, I didn't count the 9s. You change the table to ask and enter 1.9999999. Doesn't matter. Let's say I did manage to remember the exact number of 9s and I hit enter. My calculator gives me an error here. So that's equivalent to saying there's a hole. But be careful, because I think if you enter a number really close, as if 1.9, etc. wasn't really close, but you really pushed it to the limit and sat there typing 9999 for 5 minutes and hit enter, your calculator might actually calculate it and say it's 2. It's just going to round it though. All right. Simplify each function. So this is going to show us how we could determine whether that non-permissible value is going to be responsible for a vertical asymptote or for a hole in the graph. When I simplify a rational function, I factor everything first. And x squared minus 8x plus 15, I guess, factors into x minus 3, x minus 5. Would we be in agreement there? Okay. That's step 1 in simplifying a rational expression. Step 2 is to cancel identical factors. So you have 2 factors on the top, By the way, cancel identical factors means one on the bottom, one on the top. You have two factors on the top, you have one on the bottom. There are no matching factors. There's no common factor to the top and the bottom. This is it. Nothing is simplified. G of x, we factor, this would be x minus 2, x minus 1 over x minus 2. And what happens here is the x minus 2's cancel. And you get a line, x minus 1. But wait a minute. This x minus 1 cannot be g of x because x minus 1 is a line and g of x is a line with a hole in it. Let me demonstrate this to you on your graphing calculator. This is g of x, right? Look at it. It's a line, but it's got a hole in it. If I think that g of x simplifies to x minus 1, and if in fact it does simplify to x minus 1, then when I graph x minus 1, I have to get this exact same picture because that's g of x. And I don't. These two graphs are different, which means these two functions are different, which means I cannot write g of x equals x minus 1 unless I say that x cannot equal 2. As soon as I say x cannot equal 2, then what happens is at x equals 2, I get a hole. But without saying x cannot equal to 2, I don't get that hole, which would mean it would be wrong. And this is why in Math 20, you were taught to determine your non-permissible values first, because they form part of the description of the function. So what is the rule here? The rule is, if your non-permissible value factor in the denominator cancels, you get a hole. If the non-permissible value factor in the denominator doesn't cancel, you get a vertical asymptote. Okay. If the NPV factor cancels, you get a vertical asymptote. If the NPV factor does not cancel, I got that backwards, don't I? My mistake. If the factor doesn't cancel, you get a vertical asymptote. If the non-permissible value factor stays, you get a vertical asymptote. If it cancels, you get a hole. Sorry about that. Does that make sense? I'm not asking if it makes sense as to why that happens. I'm asking if it's clear what I'm saying now. Okay. So what are the domain and range? I don't even want to talk about the range of f of x. It's unimportant to the lesson, and it's not something we are even going to do. What is the domain of f of x? The domain of f of x is that x is not equal to 2, and the domain of g of x is also that x is not equal to 2 because there's a non-permissible value at 2. Okay. What is the range of g of x? Well, look at the graph. I guess I put my hole in the wrong place, didn't I? It's there. Is y defined everywhere? No. There's one place where it's not defined. And it's the place that y was approaching when x was approaching 2. As x was getting closer to 2, which it's not allowed to reach, y was getting closer to 1. And if x can't reach 2, y can't reach 1. In other words, your range for g of x is x cannot equal to 1. Now, I want to show something to you. We determined this 1, like Jason said it was 1, by looking at the graph, correct? You don't need to. What you could do is look at the simplified form of g of x and put the value of x in that you're not allowed to use, and you will get the value of y that you will never get. I know that seems weird. So if I were to put this non-permissible value in and say, you know what, I don't care. I'm going to calculate g of 2 anyway. I would have 2 minus 1, and g of 2 is equal to 1, which means this is the point we're talking about. But since x can't equal 2, this point doesn't exist. It's a hole. Make sense? Okay. We've already done this. I'll write it again. As x approaches 2, y approaches plus or minus infinity if there's an asymptote. But as x approaches 2, y approaches some y coordinate if there's a hole. Good? Example 2, determine the non-permissible value of x if 1 exists for each of the following rational functions. Well, you're going to have to factor the denominator here to see if there are non-permissible values. And while we're factoring the denominator, let's factor the numerator as well. And these are all pretty basic expressions to factor. The numerator factors into x and x plus 2. The denominator does not factor in f of x. G of x factors into x over x plus 2. Pardon me, x times x plus 2 over x plus 2, x minus 2, because the bottom is a difference of squares. H of x factors into x, x plus 2. These are all going to have x, x plus 2 in the numerator, and it's over x minus 4. K of x is x, x plus 2 over x plus 2. So what are our non-permissible values? I'm going to write them as x is not equal to for all of these. So for the last one, which is where I'm standing, x is not equal to negative 2. It doesn't matter that that x plus 2 can cancel. That x plus 2 in the denominator is part of the original expression. X is not equal to 4 for h of x. X is not equal to plus or minus 2 for g of x. And there are no non-permissible values. There are none for the first one. So all we're doing for non-permissible values is looking in the denominator. Any questions with A? Yes? Absolutely. Then we're starting to talk about the domain. And yes, I'm going to write that. X is an element of all real numbers. There's no value of x that's non-permissible. They mean the same thing. Yeah. For the functions with non-permissible values of x, determine whether the discontinuity will be a whole or a vertical asymptote. So I've just typed in here the factored forms so that I can look at them. You have them written down above. So over here we have a non-permissible value of 2 and a non-permissible value of -2. So what I'm writing here is what's happening at x equals 2 and what's happening at x equals -2. We have a non-permissible value of x cannot be 4, so here I'm going to write what's happening at x equals 4. And here I'm going to write what's happening at x equals -2. And it's a two-choice question here. At the non-permissible value, is it an asymptote, is it a vertical asymptote, or is it a whole? Well, if we start with the last one, you have a whole. Why do you have a whole? Because the rule says that if you can cancel the factors, that non-permissible value turns into a whole. And that's always true. That means at x equals 4, you have a vertical asymptote. Because the x minus 4, which produces that non-permissible value, doesn't cancel. With g of x, x plus 2 cancels with x plus 2, which means that at -2, you have a whole, because the 0 of the factor that cancels is -2, and the rule is if that factor cancels, you get a whole. And at x equals +2, you have a vertical asymptote. And then there's nothing over here for b. There's no non-permissible values. As Evan pointed out, it's defined for all real numbers. So you can't have any wholes, you can't have any vertical asymptotes. For those functions with a vertical asymptote, so there was a vertical asymptote with g of x, and there was a vertical asymptote with h of x. For those with vertical asymptotes, what's the equation of the asymptote? Well, it was the x minus 2 that did not cancel, so the equation of the asymptote is at x equals 2. It's x equals whatever the non-permissible value is. And here, this was the factor that produced the vertical asymptote, so x equals 4 is the location of it. For those functions with a point of discontinuity, which is the whole, and there was a whole here, and there was a whole here, am I correct? Okay. The whole for g of x was at -2. So the x coordinate of the point that doesn't exist is -2. How do we find the y coordinate of that point that doesn't exist? We put the x coordinate that we're not allowed to have into whatever survived the canceling to get the y coordinate. So g of x simplifies to x over x minus 2, where x is not allowed to be 2, but this should be +2, shouldn't it? No. I double-psyched myself. It is -2 because it's the 0 of the factor that cancels. So I need to put -2, even though I'm not allowed to put -2 in there. By the way, let me clean this up. Do I also need to write x is not equal to 2 because of the other non-permissible value? I would say yes. I know you could argue that since there's still an x minus 2 there, you don't need to do it, but technically you should. Anyway, we're going to put the x coordinate of the whole in for x. And I'll get -2 over -4, which is 1/2, I believe. Is that right? Okay. Over here, we're going to do the same thing. The whole will be at -2, comma, well, -2. Because these x plus 2's cancel, and if you put -2 into whatever remains, you're going to be left with -2. Any questions with D? Okay, example 3 asks us to match. So as a precursor to this question, we have to match 3 different functions with 3 different graphs. I would like everybody to factor completely all of these expressions. So that factors into x plus 2, x minus 2 on the bottom, and x plus 2 on the top. Again, the things we're factoring here for these functions are not complicated pieces to factor. The idea is if a factor cancels, like the x plus 2's do, then that non-permissible value, which would be -2, has to correspond to a whole. Well, looking at those 3 graphs, there's only one graph that has a whole. It's graph 2. But just as a check, we should have a whole at -2, and because there's an x minus 2, we should have a vertical asymptote at +2. And when we look at graph 2, sure as shooting, we have the whole at -2 and the asymptote at +2. Going along the lines of Evan's comment that if there are no non-permissible values, the domain is any real number, when you take a look at b of x, I don't even need to factor the numerator here. B of x has no non-permissible values. So it cannot, for x, it cannot have any vertical asymptotes, and it cannot have any wholes. And the only graph that is continuous from -infinity to infinity is graph 3, which means this is b of x, which by process of elimination must make graph 1 c of x, but in factored form, c of x has 2 factors in the denominator, neither one of which cancels. So you have 2 vertical asymptotes at the 2 non-permissible values, which graph 1 definitely has. So c of x is 1, a of x is 2, b of x is 3. Okay, so now we have to match things again. We've got a graph 1 that has a hole and an asymptote. We have graph 2, which simply has a hole. We have graph 3, which has 2 asymptotes. So we're going to factor k of x. And I can't remember how this is printed on yours. Are the graphs on the side? Okay, so the way I've got it up here, I just put it this way so it would fit, but I hope you understand that k of x is not graph 1 necessarily. That's the way they are. Actually, let's do this instead. I knew I copied it in a different page. So k of x is x squared plus 2 over x minus 2, x plus 1 is how the denominator factors. Well, that's got to be graph 3. I mean, without even looking at where the asymptotes are, we have 2 factors in the denominator, 2 linear factors that do not cancel with anything in the numerator. So we have to have a vertical asymptote at 2, and we have to have one at -1. without looking at the numbers, graph 3 is the only one that has two vertical asymptotes, but looking at the numbers, they match the non-permissible values. So this is k of x. L of x factors into x minus 1 over x plus 1, x minus 1. We have an identical factor on the top and the bottom that cancels. So we have one factor that cancels and we have one that doesn't, which means you have a hole and an asymptote. The hole should be at the place where the zero of the factor that cancels is. So since the x minus 1 canceled, we need a hole at 1. Since the x plus 1 didn't cancel, we need a vertical asymptote at -1, which makes this graph L of x. And by a process of elimination, this is m of x, but I want to talk about what's going on here with m of x. When we factor this, it factors into x minus 2, x minus 3 on the top, and on the bottom, we have 3 minus x. You are only, this is such an important rule from 20-1, and we did it in trig and other areas. You only ever cancel if there's a factor that's canceling, which means it has to be in brackets, multiplied by everything else on the top, and multiplied by everything else on the bottom. But it has to be identical. X minus 3 and 3 minus x are not the same. How many of you know the kind of shortcut workaround here? Okay. If you don't, ask yourself what you can do to one of those factors to turn it into the other factor. The shortcut is to cancel them and throw a negative somewhere. But the reason that works is because you can, in this example, factor a -1 out of the 3 minus x on the bottom. The 3 becomes negative, the negative x becomes positive. Now we're off and running. So what m of x actually simplifies to is negative x minus 2, as long as x is not equal to 3. Because even though we canceled that 3 minus x, that x is not equal to 3 is a non-permissible value that follows all of the work. So this is, when you take a look at this, this is negative x plus 2, which is a line with a y-intercept of 2 and a slope of -1. And you look at graph 2, the y-intercept is 2, the slope is -1, but at x equals hopefully 3, there's a hole. Any questions with example 3? Scroll down. I'm sorry. However you decide to write this m of x, if you were doing a written response, whether you write m of x equals negative x plus 2 or negative of x minus 2, you need to, without a doubt, everyone, include the x is not equal to 3. Is that okay, JV? Okay. Grant? We have one example left, and I've thought of many different ways to teach this to you, but there's one other detail that we need to know. Okay, so if you have a rational expression as an equation of a function, we know that if you have a hole or a non-permissible value of any kind, whether it's a vertical asymptote or not, that factor appears in the denominator of the rational function. So looking at this graph, you see that there is a vertical asymptote. We'll just go with y. There is a vertical asymptote at -4. No, at -2. Which means that at x, that the factor is x plus 2 in the denominator. Okay. I kind of jumbled my wording there. Let me repeat that. Whatever the zero of the vertical asymptote is, whatever that vertical asymptote location is, that's the zero of the factor that has to be in the denominator. So specifically in this case, if you have a vertical asymptote at -2, you must have a factor in the denominator of x plus 2 to produce that non-permissible value. If you have a whole at a particular value of x, then that value of x has to be the zero of another factor that's in the denominator. Because, to be specific, in this question, if x is equal to 3, which is the x coordinate of the whole, you're not allowed to do that because there's no point there. So why mathematically are we not allowed to use x equals 3? Because in the denominator we have x minus 3, and you put 3 in for x, you get 0 in the denominator, which means you'll be dividing by 0. But we have also learned that if there's a whole, you need an identical factor in the numerator to cancel with the one in the denominator that produces the whole. If you graph this, it will not give you that picture though. There's another piece of the puzzle that I haven't revealed to you yet. And just to demonstrate that to you, if we were to graph this, and you need to be particularly careful here with how you enter it, I would go so far as to say when you're entering rational functions, you need a set of brackets around the entire top, and you need a set of brackets around the entire bottom. So I actually need to put for the bottom bracket and then bracket x plus 2 n bracket x minus 3. I don't know because I never, and then n bracket again. I never used the TI-84. With the TI-84, when you're in math print, does it actually create a fraction and you type on top and bottom? I don't think it does, eh? So you need all these brackets. Double check, x minus 3 on the top. That looks good. Zoom 6. Not even close. First of all, that thing that you're looking at on the graphing calculator appears to have a horizontal asymptote that's on the x-axis, right? There will be a hole there at x equals 3, but it's not right. You can even see the y-intercept of this graph is 2 that we're after. The y-intercept here is 0.5. It's not right. But you are not going to try to take this thing that's on your graphing calculator and translate it. You're going to use the final piece of the puzzle, which is this, that an x-intercept has to be represented by a factor in the numerator. If this graph crosses the x-axis at -4, then you need to have x plus 4 in the numerator. And the reason for this is quite simple. An x-intercept has a y-coordinate of 0. So ask yourself how this, not even this, ask yourself how, if you have y equals a numerator over a denominator, how can y equal 0? The only way y can equal 0 is if the top of this fraction is 0. It's the only way you're going to get 0, 0 over something else. So how do we make the top of this 0? Well, if this were 0, then the top would be 0 and the whole thing would be 0. So this leads us to the x-intercept. Why is there no x-intercept then at 3? Why is there no x-intercept at 3? I just said that any factor in the numerator produces an x-intercept. Fine. It cancels. So now the rules get more complicated. If you have a factor in the denominator that does not cancel, I call it a lone factor. There's a vertical asymptote. If you have a factor in the numerator that does not cancel, you have an x-intercept. If you have identical factors in the numerator and denominator, then you will have a whole. Now, so we're done with this question. Any questions with this specific example? I feel as though, because the Math 30 diploma exam can get downright mean at times, I need to say something, that there's an exception to everything I've said. If you had the following, Let's just say we have y equals x, x plus 2. I've already factored it, x minus 1 over x plus 4, x plus 2. Okay, if I had this, yeah, we have time. I think this is worth the effort. And I say to you, tell me about the X-intercepts, the vertical asymptotes, and the holes. Because this cancels, we would have a hole at -2. And if you wanted to determine the y-coordinate of the hole, you'd put -2 into everything else that doesn't cancel. And if I put -2 on the top, I'm going to end up with 6 on the top. And on the bottom, I'm going to end up with 2. I believe you're going to get 3 for a y-coordinate, which is really not the point of what I'm doing here. But if you put -2 on the top, let's just check. -2 times -2 minus 1 over -2 plus 4. You get -2 times -3, which is positive 6 on the top. You get positive 2 on the bottom. 6 over 2 is 3. So you'll have a hole there. You will have a vertical asymptote at x equals -4. And you will have x-intercepts at x equals 0 and 1. Just let that roll around upstairs in your brain for a second and see if that makes sense. Okay. Everything is perfect here. It follows all of these rules that I've just kind of summarized, but I already did that. What if it were that? What if it were over x plus 2 squared? What would happen is this would simplify after you do some canceling to x minus 1 over x plus 4, x plus 2. So you have a factor that cancels, but it's still in the denominator. Let's take our graphing calculator and graph this thing at the top, which I had said earlier you need to have a set of brackets around the entire top. I guess that's not true because you're dividing. So it's multiply, 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 divide. So you don't really need this first part to be in an entire set of brackets. We have x plus 2. Then we have another factor on the top of x minus 1. Remember, we want to factor the original expression. Because if there's a hole maybe that is because of canceling factors, we might not see the hole. And this is over. We definitely need brackets around the entire bottom here. Another set of brackets for the x plus 4. And then we have x plus 2 squared and close the brackets. That's a lot to track with the brackets, but I'll double check it looks okay. We'll go zoom 6. What I'm really interested in, I know I'm going to have a vertical asymptote at -4. I know I'm going to have x-intercepts at 1 and 0. And believe it or not, they're in there. But do I get now a hole at -2 or a vertical asymptote at -2? I get a vertical asymptote, don't I? So if you can cancel a factor on the bottom, but you can't totally eliminate it, any factor that survives and is still on the bottom is a vertical asymptote. I don't want you to think because we canceled the x plus 2 here, it's a hole. You might ask yourself this question, what if it were the other way around and the x plus 2 were squared on the top? And I don't know that this is absolutely important, but I'm going to show this to you. Is a speaker hissing? No? So first of all, this is my thinking. If it's the other way around and we have the squared on the top, my way of thinking is it shouldn't matter. -2 is still non-permissible, right? And you might say to yourself, well, what's going to happen here is we're left with a survival of x plus 2 on the top, so it must be an x-intercept. How can it be an x-intercept when it was non-permissible? So if we take a look at this graph, did I square the top? No, I did not. So do I have my asymptote at -4? Yes. Now, what's going on at -2? It looks like an x-intercept, doesn't it? It really does. It's a pretty wild graph. I'm guessing the part to the left of that asymptote is way up high. Looks like it's going through -2, doesn't it? But it's not. There's a hole. Which means if you have a factor that cancels partially, but it's left on the top because you had more of them on the top, then what you get is a hole at where the x-intercept would be. I don't know if we'd be able to see it. I'm going to turn my axes off. And I'm going to try zoom decimal. Yep, it's a pretty big hole, but that's just my calculator. It's really a tiny hole. But the bottom line, everybody, to make it simple, lone factor on the top, x-intercept. Cancel a factor on the top with the bottom, hole, whose y-coordinate can be found by putting the non-permissible value of x into whatever's left. Lone factor on the bottom that doesn't cancel, vertical asymptote. So some things that you need to remember to be successful here with this set of practice problems. We have not talked about horizontal asymptotes. Don't worry about it yet. There's a totally separate kind of deal with horizontal asymptotes. I hope that made sense. Give me a second to take attendance, and then I'll come around and I will check on your progress.